In this video, we're going to go over a couple of very important trigonometric limits that you're going to see all over the place, and they'll be very useful in solving future limit problems that we'll take a look at. The first is the limit as x tends to 0 of sine x over x. We plug in 0. When we look at the numerator, as x goes to 0, it looks like sine of x should also go to 0, right? Because if you remember the way the sine graph looks, here's 1, here's negative 1, this is pi over 2, this is pi, and this is negative pi over 2 here. As you right around 0, as x gets closer and closer to 0, sine of x also seems to get closer to 0. And of course, in the denominator, as x goes to 0, x goes to 0. So this seems to be an indeterminate form. But as I'm going to show you using the calculator, you'll see that this actually equals 1. So the limit as x tends to 0 of sine x over x is actually 1. I'm going to go ahead and pull up the calculator. So I have the calculator pulled up. I'm going to go ahead and enter in here. Enter sine of x over x. And we're going to zoom in. Okay. So you'll see for negative values of x close to x equals 0, you have like 0.977 when x is negative 0.37. And as you get closer and closer to 0, you see that sine of x over x, which is what f of x is here, gets closer and closer to 1. And at x equals 0, it's undefined. But once you go to the right of x equals 0, say x equals 0.1, it's once again very close to 1 and gets further away from 1 as you move to higher and higher values of x. But around 1, it looks like around x equals 0 looks like y is very, very close to 1. So that shows you the limit as x tends to 0 of sine x over x is 1. And we'll later prove this limit using the squeeze theorem, and that's a subject for another lesson. But this is a very important limit. Another very important limit is the limit as x tends to 0 of 1 minus cosine of x over x. And looking at the numerator, looks like we have 1 minus cosine of 0 is 1. Denominator, we have 0. This looks like it's an indeterminate form as well, but like I said in the indeterminate forms video, that doesn't necessarily mean the limit doesn't exist. It just means we'll have to do more algebra to figure out what it is, whether or not it exists. Okay, so limit as x tends to 0, 1 minus cosine of x over x, just rewrote it here. We're going to now multiply both numerator and denominator by 1, but a very special case of 1, which is 1 plus cosine of x divided by 1 plus cosine of x. And this is called a conjugate of 1 minus cosine of x. You probably remember that term from your pre-calculus classes, but Let's multiply both numerator and denominator by the conjugate, or 1 plus cosine of x. See what happens. So 1 minus cosine of x times 1 plus cosine of x is 1 minus cosine squared of x. This is also the same thing as, this is equal to 1 minus cosine of x squared. So those are the same thing. Denominator, we have x times 1 plus cosine of x, and just rewrote it here. X times 1 plus cosine of x. Alright, so 1 minus cosine squared of x is sine squared of x. If you remember from your Pythagorean identities, sine squared x plus cosine squared x equals 1. You may also see it as sine squared theta plus cosine squared theta equals 1, but theta and x are just variables. Alright, so this means that sine squared x, if you isolate sine squared x, so looking at this expression here and subtracting cosine squared x from both sides, get sine squared x equals 1 minus cosine squared x. So where you have 1 minus cosine squared x, we can just write sine squared x. Of course, you still have the limit outside here. Same thing here, we still have the limit as x tends to 0. So numerator, we've rewritten 1 minus cosine squared x as sine squared x. Denominator, we still have x times 1 plus cosine of x. So sometimes when you see an expression like this, you'll see factors. You'll find that you may know the limit of one of the factors, and in this case you actually do. We just went over what the limit of, as x tends to 0, of sine x over x is. And you can see that sine squared x is the same thing as sine x times sine x. Okay, so this is the same thing as sine x times sine x. And this denominator is the same thing. Of course, it's x times 1 plus cosine of x. But what we can do is we can split this up here. This is the same thing as the limit as x tends to 0 of sine x over x. Because remember, the limit of a product is the same thing as the product of limits. So the limit as x tends to 0 of sine x over x times the limit as x tends to 0 of sine x divided by 1 plus cosine of x. And we just saw that this limit is 1, right? So what's this limit? Well, as x goes to 0, sine of x goes to 0. As I kind of showed you from this messy graph here, as you get closer and closer to 0, as x gets closer and closer to 0, sine of x gets closer and closer to 0, and that's approaching from both sides. Okay, so we have 1 times 0 divided by, but what happens to the denominator? Well, as x tends to 0, cosine of x tends to 1. We have 1 plus 1. So 1 times 0 over 2 is 1 times 0, which is 0. So this might not be visible here, but this is the limit as x tends to 0 of 1 minus cosine of x over x is equal to 0. So that's the limit as x tends to 0, 1 minus cosine of x over x equals 0. So the bottom line from this lecture is this limit here equals 0, and the limit as x tends to 0 of sine x over x equals 1. And we'll work some examples making use of these two important limits along with some of the properties of limits we talked about earlier.